Hello everyone, in this video we'll be solving an interesting problem number 300, longest increasing subsequence. The problem statement is, given an integer array nums, we need to return the length of the longest strictly increasing subsequence. The numbers in the subsequence do not need to be adjacent to each other in the input. It can be at different positions, but as long as the values are increasing, it can be included in the subsequence. For instance, in example number 1, with this as our input, the longest increasing subsequence is of length 4 with numbers 2, 3, 7 and 101. As you can see, these numbers are not adjacent to each other. Each number appears to the right side of the previous number in the array. The problem statement is straightforward, but the optimized solution needs a bit thinking. So let's switch to whiteboard and start discussing the solution. Let's start with discussing how we can solve this problem using brute force. In the brute force approach, we'll try to build all possible combinations with each of the number in the input array to see if we can include it in the longest subsequence. Let's do a quick dry run starting with the first element in the array, which is 0. Next element in the array is 1. The value of 1 is greater than the previous number, which is 0, so it can be included in the subsequence. Even though the value is greater than the previous number, we have a choice. We may or may not include it. Let's say we include it in the subsequence. Then the subsequence will be 0, 1. If we continue to build the tree with that option, the next element is 0. Now we'll repeat the same comparison with the new value 0 with the previous value that was added to the subsequence, which is 1. Between the two, the new value is not greater, so it cannot be included in the existing subsequence. So we only have one option here to not include 0 in the current subsequence and move to the next number, which is 4. We'll repeat the same comparison to check if the value 4 is it greater than the last element, which is 1. Yes, it is greater, so it can be included in the current subsequence, increasing the length to 3. Similarly, we'll try to build the other combination on the right hand side of node 1 where we did not include the next number to see if we can build a wider or a longer subsequence. And at any given point of time, if we can't include the number in the existing subsequence, we will compare the current subsequence length with the max length, which is a global variable, and whichever is going to be the larger number will be saved into this variable. Once we have iterated through all of the combinations, at the end we can return the max length as our output. As we have a decision to make at each number whether to include it or not to include it, the overall time complexity of this solution is going to be O of 2 raised to power n, where n is the number of elements in the input array. And the space complexity is O of 1, as we are only using a couple of variables during the recursive calls and the global variable max length to record the maximum length of the subsequence. As the time complexity of this approach is very high, so let's discuss an optimized solution with better time complexity. In the brute force approach, when we were trying to build an entire tree and deciding if we should include the next element to the existing subsequence or not, if we would have continued, there would be a lot of combinations which would have processed multiple times. To avoid those duplicate calculations, we can use a dynamic programming array to store the maximum or the longest subsequence between two numbers and use it to do the lookup if we are trying to extend that subsequence by adding more elements. Let's run a small simulation to understand this approach better. If I look at the first two elements in this array, they are in the increasing order and can be part of a subsequence. Now let's say I want to add one more element x to this subsequence. Technically, the criteria is that the value of x should be greater than all of the elements in the subsequence, but instead of doing that comparison, we can just validate if x is greater than the last element in the subsequence, which is 1. Let's run a quick iteration. The next element in the array after 1 is 0. As 0 is not greater than the last element in the subsequence, it cannot be included. After that, the next element is 4. As 4 is greater than the last element 1, it can be included in the subsequence. So the new subsequence would have 0, 1 and 4 in it. When we created the subsequence with elements 0 and 1 in it, its length is 2. So we can save its length in the corresponding position in the dynamic programming array. Now with the new addition of an element to the existing subsequence, I can just look up the size of the longest subsequence from the DP array, increment it by 1 because we are adding one more element, and save it at the same index as 4. So with that logic, at I is equals to 3, we'll save the value 3 as that is the longest subsequence so far. Similarly, we'll continue the iteration on all of the elements in the array and compare its value with the previous elements in the array to decide if it should be included in the subsequence. Let's run a few more simulations and use a proper dynamic programming array to maintain the records how it will be updated as we continue the iteration. As we have already calculated the values for index 1 and 3, I'll just pre-populate them in the DP array. Now let's try to process the next element in the array, which is at index 4. The value is 2. We'll start with comparing it with the first element in the array, which is 0. As 2 is greater, it can be included in the subsequence starting with 0, then the next element will be 2. The longest subsequence at index 0 is 1 because it is the only element. So after adding 2, the length will be increased by 1. So we can save that in the DP array at I is equals to 4 because that is the longest so far. This is the longest subsequence so far, but it can change as we try different combinations. Now we'll increment the pointer and compare 2 with the next element, which is 1. As 2 is greater, it can be included in the subsequence which has 1 in it. So we'll take the corresponding value in the DP array, increment it by 1, and compare the results with the existing value at I is equals to 4 in the DP array. As 3 is greater than the existing value, we'll override it and continue with the next run. The next element is 0. If you compare 2 with 0, as 2 is greater, we can include it in the subsequence. It would be similar to what we processed earlier. As each element is a subsequence in itself, the default value will be 1. Adding 2 to it will make it 2, but it is not greater than the existing value in the DP array. So we'll skip it and continue with the next combination. The next number is 4, which is greater than the current number 2, so it cannot be included. So there is no processing needed here. We have processed all combinations with 2 as the last element. Now we'll increment the pointer to try it with the next number, which is 3. We will repeat the same operation we did with 2, but this time we'll try to add 3 to each of the subsequences that have already been established. So we'll compare the values and see if 3 is greater. If yes, then we'll take the corresponding length from the DP array for each of those values, increment it by 1, and save it in I is equals to 5 position. Instead of trying all combination, let me just process the last one, which will yield us the result that we are looking for, which is index 4 value 2. As 3 is greater than 2, it can be included, so we'll take the corresponding value from the DP array for I is equals to 4, increment it by 1, and save it in the DP array if it is greater than the current value. And during the iteration, every time we are overriding the value of the DP array at any index, we'll compare that value with the max length variable as well, which is at a global level. We'll only save the longest or the highest value in this variable, which will be our output after all of the iterations are complete. In other words, when we process the last combination of adding 3 to the subsequence that ended with 2, the value 4 will also be saved to the max length variable. With this solution, our time complexity is improved to O of n square as we are running two nested iterations. One is to identify the last element in the array, and the next one is to compare it with all of the elements before it to see if it can be included. And the space complexity is O of n as we are using this dynamic programming array to record the longest subsequence for each of the element in the array. I hope you were able to understand the explanation. Let me show you how we can implement this using C#. In the C# solution, I start by adding a validation to make sure that the length of the input array is always greater than 0. If not, then I'm returning 0. After that, I'm initializing a new array DP of type integer and length same as the nums array. Next, on the next line, I'm starting a for loop to iterate through all of the elements in the input array. We will use the value that I is pointing to check if it can be included in any of the existing subsequences. Inside the loop, I am starting another for loop that will be used to identify the last element in the current subsequence and then compare it against the newer value. If the value that I is pointing is greater than the value that j is pointing, it means the new element can be included in the existing subsequence. So I'm comparing the value of I in dp array with the value at j plus 1, and whichever is higher will be saved into the dp at the ith position. As we are using the max length to record the maximum subsequence that we built, I'm using the math.max operation to compare dp of I with the previously calculated max length and saving the higher value into the variable and return at the end. This code, when submitted on LeetCode, beats 21% of the submissions in terms of runtime and 35% in terms of memory. Thank you for watching this video. I hope you were able to understand the explanation. The details to access the source code is available in the description below. Feel free to check that out, and I will see you in the next one. Thank you.